Welcome to Saitechinfo channel, my dear students. In this tutorial, I'll be discussing about the chemical properties of nitrogen family. The common oxidation states which are available in nitrogen family are -3, +3 and +5 oxidation states. For example, let us consider nitric acid HNO3. Let us calculate the oxidation number of nitrogen in nitric acid. We know the oxidation number of hydrogen is +1 and oxygen is -2. So 1 plus X plus 3 into -2. And for any neutral compounds or molecules, we take the oxidation number as 0. Therefore, X and this is +1, this is -6 is equal to 0. So, X minus 5 is equal to 0. It means X is equal to +5. So, the oxidation state of nitrogen in nitric acid is +5. Let us consider HNO2, that is nitrous acid. So, here let us find out the oxidation state of nitrogen. So, for hydrogen it is +1, for oxygen it's -2. So, the neutral compound, so its oxidation state is 0. So, 1 plus X plus 2 of -2 is equal to 0. Therefore, 1 plus X minus 4 is equal to 0. So, X minus 3 is equal to 0. X is equal to +3. So, in the case of nitrous acid, the oxidation state of nitrogen is +3. Similarly, let us work out for ammonia. Here we have +1 for oxidation state of hydrogen and put X for this. So, X plus 3 is equal to 0. So, X is equal to -3. So, in this case, the nitrogen has the oxidation state -3. So, likewise, the common oxidation states in nitrogen family are -3, +3 and +5. Let us consider phosphorus in PCl5. So, the phosphorus in PCl5, its oxidation state is +5 because for chlorine it is -1, therefore it is +5. Similarly, for PCl3 it is +3. So, the -3 oxidation state decreases down the group. So, nitrogen, phosphorus, and we have arsenic, stibine, then bismuth. So, down the group what happens, that is the -3 oxidation tendency decreases. So, you cannot have that is -3 oxidation state down the group. And particularly in case of bismuth, it shows the metallic behavior. So, this -3 oxidation state decreases down the group. Why? because of the increase in the metallic behavior. What do you mean by a metallic behavior? That is electron releasing tendency. So when it releases electron, where is the question of retaining the electron? And that is why -3 is rolled out down the group. It is decreasing. Is it clear now? Right. Now, let us check the stability of a +3 oxidation state. That actually increases and the +5 oxidation state decreases. It is because of the inert pair effect down the group. So the inert pair effect decreases down the group. It means, what do you mean by inert pair? Let us analyze the electronic configuration. Let us go back and we have got the various shells here. For nitrogen, there is no D block, and for phosphorus also there is no D block, whereas the D block starts only from arsenic. Okay, so let us write down the electronic configuration of nitrogen in a box model like this. So nitrogen is 7. So let us consider the outermost shell 2s2, 2p3. So it can be indicated by a box model like this, 2s2. So we have a lone pair of electrons and 2p3. So each one electron. So this is half filled. So 2p3. So these are called the valency electron, that is a bonding electrons here. Bonding electrons, they involved in bonding. Whereas this is called lone pair of electron, that is non-bonding electrons. Okay, right. Now, see, the stability of +3 oxidation state increases due to the inert pair effect. So, the +5, that is, in all cases you have 2 plus 3. For example, this is completely filled and this is filled, and this is 6s2, this is 6p3. What about this? This is completely filled 4d10 and 5s2, whereas 5p3. And similarly, that is 3d10, 4s2, 4p3, 3s2, 3p3. So in all these cases, the unfilled orbitals are p, where 3 electrons are available, and that is why it has the tendency to retain the +3. Are you able to follow? Whereas +5 is ruled out, that is +5 state decreases. It cannot take the lone pair electron outside. So that lone pairs are almost, that is, may not be available for bonding. And the stability here for this +3 oxidation state increases because of what? The effective nuclear charge. It will be pulling the electron like anything, and the 2 electrons may not be available. So that is why +3 oxidation state increases. Its stability increases. And here, nitrogen is restricted to the maximum valency. Nitrogen is restricted to the maximum covalency of 4, since it has only one s and 3p orbitals. So it has one s orbital and 3p orbitals. Now, when you look at the nitrogen, it has got some unique nature, and that is why it is studied separately as anomalous behavior properties of nitrogen. Is a very important topic. So, the uniqueness, the unique properties of nitrogen, okay, from the rest of the members, because of its smaller size and high electronegativity. We know down the group, electronegativity decreases. So since nitrogen occupies the top position, it is more electronegative. Down the group, electropositivity increases. So the high electronegativity which is at the top of the group that is occupied by the nitrogen, that brings a unique property for nitrogen. Likewise, high ionization enthalpy and the absence of d orbital, that is also a very important character. Then it has the tendency to form p pi multiple bonds. What do you mean by this? For instance, let us consider nitrogen. By itself it can form, that is, pi bonding. There is one sigma bond and two pi bond, and it can form with the carbon also, like C triple bond N, cyanides. Okay, so such type of a p orbital, the pi bond of p orbital, the pi bond of p orbital, that is responsible for the formation of multiple bond like this. Whereas heavier elements do not form such p pi multiple bonds because their orbitals are large and they may diffuse and they cannot form effective overlapping. Whereas in the case of nitrogen, it can form, and that is why we have got the multiple covalency here. Then nitrogen exists as diatomic molecule with the triple bond, as I already mentioned. Bond enthalpy is also very high, that is, the energy required to break the bond is very high. Then, even though the nitrogen, triple bond nitrogen is much stronger than any other bonds available in that group, however, the NN single bond, let me take the single bond alone, that is weaker than the phosphorus single bond or arsenic single bond or stibine single bond. It is because of what? The high inter-electronic repulsion. Okay, there is an very high inter-electronic repulsion because of the non-bonding electrons. We have already seen nitrogen had a lone pair of electrons. Okay, so that is responsible for what? The repulsion, and that results the smaller bond length also. So the catenation tendency means chain forming tendency is weaker in nitrogen, whereas phosphorus and other compounds can form. Then nitrogen cannot form d pi p pi or d pi multiple bonds because they don't have d orbital. Okay, right. Then let us discuss the reactivity towards various elements like hydrogen, oxygen, halogen, metals. All these elements of nitrogen family can react with hydrogen to form the respective hydrides. For example, NH3 element, E represents here element, that is nitrogen, phosphorus, bismuth, antimony, etc. So nitrogen, phosphorus, arsenic, bismuth, stibine, that is antimony, and bismuth. Okay, so it can form NH3, this is ammonia, PH3, this is phosphine. Okay, so arsine, that is ASH3. Okay, so likewise it forms various hydrides. Okay, right. And their hydrides, their stability decreases down the group. Reducing character also increases here. Then basicity decreases. Okay. Let me talk about the oxides. So all these elements can combine with the oxygen to form, that is, the relevant trioxides and pentoxide. But the +5 oxidation state is more acidic than +3. For example, phosphorus pentoxide is more acidic than phosphorus trioxide. It means the acidic character decreases down the group. Acidic character decreases down the group. Okay, so it means that is, see, let us consider the that is N2O5 and that is AS2O5. So in that case, the acidic character of AS2O5 is less than that of the N2O5. Okay, So the nitrogen based oxides are more acidic, and especially in +3 oxidation state. Then halogens. So nitrogen can form, that is nitrogen trihalides and pentahalides. But the problem here with the pentahalide, there is no d orbital, so nitrogen cannot form NCl5. It can form NCl3, but it cannot form NCl5. That is pentahalide is ruled out. Whereas in the case of phosphorus and other elements, they can form phosphorus trichloride PCl3, phosphorus pentachloride PCl5. So this is possible. Okay. And +5 oxidation state is more covalent than +3 oxidation state in case of halides. Then when we talk about the metals, the combination of these elements with the metal, they exhibit -3 oxidation state. For example, you have calcium nitrite, okay, that is calcium nitrite. So for nitrogen it is 3, so Ca3N2. Are you able to follow? Why? Because the nitrogen has a valency here -3 and the calcium has +2 oxidation state. So this has +2 oxidation state, this has -3 oxidation state. Okay. And then calcium, why? Because the calcium is more electropositive, whereas so when it is compared with the calcium, its metallic behavior is less. And similarly, calcium nitride and calcium phosphide Ca3P2, calcium phosphide. Sodium arsenide means that is Ca3 what? Arsenide As2. Similarly, Zn and Zn3 antimonide. Antimonide means Sb2. Okay. And similarly, magnesium bismuthide. So magnesium Mg3Bi2. So you have to be familiar with certain types of metal compounds. Okay, metal based nitrogen elements. Right. So thank you very much for watching this video.